Is that it's now printing something, but it doesn't know where to, or let alone which printer model and these kind of things. So that's a really cool thing. The last case study I want to present is concerning USB security. So my machine is standing there right now, and I have no idea what it's doing. Right? I'm not present at my machine. It's actually it's locked, and there's no reason that it does anything via USB, because, how could I ever plug something in because I'm not present? The machine is locked, I'm away, yet if you plug anything into the USB port, then Linux will happily talk to the device. Linux will happily load any driver that the device tells Linux to do, and it turns out there's a lot of drivers in this current new Linux operating systems, and it turns out you can program USB devices very cheaply to be whatever they want. And the quality of the drivers of certain USB devices is questionable at best. So we have this large attack surface sitting there waiting to be exploited for no good reason, because the argument is that it doesn't make sense for the operating system to load any driver while you're not even present at this machine. You can make this argument, and there's few instances where it does make sense to do so, but for most cases, my argument is that we should not load any random driver off the disk when somebody's plugging in a device when we're not even present at the machine. And it gets worse, because there's a USB IP driver, so worst comes to worst, you don't even need physical access. You can do that remotely in the worst case. So the question to us is, if we wanted to protect from this threat, so we are building an operating system, we're GNOME right now, and we want to protect against some random dude putting in a USB pen drive or a USB device, and then my kernel loading weird drivers, and then the device interacting with these drivers. So what questions do we ask ourselves now? I would say that we need to find out, when do we use USB, and more importantly, when do we not? And we need to find out who else uses the USB, and we don't even know about it. And we need to find out, in which stage we are as a system, and then act accordingly. So USB is dangerous. it's being pointed out that my time is running out. So there's a lot of USB issues. It is an issue. I'm not making this up. I have a wild fantasy, admittedly, but this is not necessarily a fantastic thing. It does exist. People do exploit things via USB. And turns out that Linux can indeed stop USB from, being talked to. So we can indeed stop USB devices from having access to the kernel thing. And this is prototypical now. So the first two things were real software that exists, and this is now more future-like what we could or should do. So Linux allows for blocking certain devices on certain ports. We have all the infrastructure ready. Now we need to tangle it up. We need to wire it up to the operating system, to the desktop, to make this decision as to when to block the whole USB stuff and when not to block. And one simple case could be to just lock the USB down when the screen is locked. That would be the trivial thing to do. And we're not there yet. While we have the options of doing so, there is no logic that actually does it yet. And I think we need to investigate some brain power into finding out, when to actually do the whole locking thing and when to unlock. So I have a few more demo videos of how this could work, but I skipped that in the interest of the schedule, and also to keep something for the discussion for later when we are in the hallway. And with that, I want to thank you very much for your attention. I know it's been a bit fast from my side, but I think we still have some time for questions if there are any. In that case, thank you very much anyway.
We really have a little bit time for questions. У нас есть совсем чуть-чуть времени на вопросы. Вопрос? Just a moment. maybe I'll go there with my microphone. Your question?
Hi, thank you. And my question is, why do you have to put all dependencies in your container? They are duplicated in the system, and the space isn't a piece of rubber.
Why do we put what in the system?
Dependencies, all the dependencies
Dependencies,
for application.
All right. So this is a twofold argument. One is you want to have the application bundle. You want this to work. So the alternative, if you wouldn't bundle up all the dependencies, then you would somehow need to provide these for the application, right? And then you would need the host operating system to have all those weird dependencies, and that's actually what we're having now. Like status quo is that if you want to install some applications, right now you need to provide all the dependencies. And this turns out to be complicated for some people. But, so you are, from what you've said, you seem to be worried about the space. The space is not an issue though, because OS3, the way OS3 works, is it deduplicates these files if they exist anywhere else. So it's a non-issue. Your concern is not valid here because OS3 takes care about that. So if you have two applications using the same library, the very same library, then it exists only one on the disk because of the way of how OS3 works. It's like the Git of large binaries. So it's a non-issue. The other part of that question is that common libraries or common dependencies are shipped in their own, say, bundle. So Flatpak has this concept of two images that you have to provide. One is the so-called runtime, and the other is the application bundle itself. And common libraries like GTK, for example, or OpenSSL maybe, actually, I don't know. But some common libraries are in the runtime, or are supposed to be in the runtime. So you don't have to provide this with your application image, because you expect that to be present in the runtime already. Right, it's a good question.
One more question. You said
Sure.
that the library was not duplicated, but used by all the Flatpak applications. For example, if I tag OpenSSL library into my Flatpak, and other Flatpak shells also the OpenSSL library, it will be shared between the Flatpak, yeah?
So the question is whether a customly built OpenSSL, for example, will then be shared by other apps which are Flatpak.
If I tag some malware, for example, into my OpenSSL and back into the Flatpak, will other applications share my malware OpenSSL?
Right, and in particular, if I put some malware into my library, will other Flatpaks pick it up? The answer is no, because the way OS3 works is it basically hashes your file, and then it addresses the file by the hash. And if you provide another file, it will have a different hash, and then other Flatpaks will not see it because they still require like the original thing. So yeah, that's not getting there. And yes, if you were able to compile the same library bit by bit, the very same way as the other applications, then yes, you will share these files. Turns out, in practice, we're not there yet to have reproducible builds. We're working towards having that, but the likelihood of you compiling the very same bit by bit binary as the other image is still low, too low. We need to address this, though. We need to work on reproducible builds. But that's the story for a whole other talk. Or maybe? All right, I couldn't understand so well because you were talking not loud enough. How about we discuss this in the break? Approach me, because I think we're being shut off now. All right, thank you again for your attention. It's been a pleasure, and I'm looking forward to talking to you.
Ну, что внутри, не ясно. Это бывает просто даже не в опыте, а в том, что нужно знать какой-то маркетинговый, не знаю, что внутри. На самом деле есть преимущества, непонятно технологии. Здесь не про контейнер. Да, он говорил, что это уже Докер — это классная технология, но без своих целей.
Okay, so our next talk is distributed operating system image risk testing from Leonard Pottering. Leonard, please.
Okay, can you hear me? Does it work?
It doesn't. Okay, now it works. Okay, hi. I'm Leonard Pottering. You might know me from System.me, Pulse Audio, and these kind of things. But today I'm going to talk about something completely different. It's a project, a side project that I started. It's called CA Sync. It's going to be a fairly technical talk, but I hope you guys are technical people, so that's hopefully not going to stop you from understanding what I'm saying. CA Sync is a new tool I've wrote that is relatively generic and useful. I'm going to talk about both the use cases for this, but also the part that is particularly interesting to me, at least, which is the lower level underpinnings, like the actual algorithms that are below it. Yeah, CA Sync is something I started a year ago as a side project to System.me, and I think it's kind of nice to use, especially in the world that we live today, and with containers and with IoT images, but it has uses beyond that. So now this thing stopped working. I mean, it has found everything, it just doesn't switch. Now it works. Thank you. Maybe it does. Maybe it's something about the distance or something. Anyway, so CA Sync, that's a tool. What is that? The name stands for Content Addressable with CA plus rsync, right? rsync, everybody of you probably, does anyone not know rsync? Everybody knows rsync, right? And you know most likely rsync as this tool that you can use to synchronize directory trees across systems, right? rsync sounds like a relatively trivial tool, right? It sounds like something that you could hack, like if you don't know much about computer science, it doesn't sound too complicated, right? Like it sounds a little bit like you could tar it up on one side and untar it on the other side, and that's already what it is. But that's not true. rsync actually has some really interesting computer science inside of it. And my tool CAsync basically takes inspiration from rsync, right? It takes inspiration, the actual rsync algorithm in rsync, and uses it for something different. The content addressable, by the way, is like that's a generic term of the logic behind Git, right? Everybody of you knows Git. Anybody who does not know Git, all of you know Git, right? It's this version control thing. But actually the logic behind Git, you know this thing with the hashes where you have a hash and that identifies some kind of object, and the object hashes again this hash, so you have a secure scheme how you can address things and how you can verify things, right? So CAsync is a combination of these two ideas: Git-like content addressable file systems and rsync kind of synchronization. Okay, it still doesn't work. Okay, I probably have to do my talk on this side of the stage. So, what is it actually? I say CAsync is short for Content Addressable Data Synchronization Tool. It's a file system tree synchronizer, much like rsync, for cases where you have many similar trees, which is a little bit different from rsync. What does that mean to have many similar trees? It basically means that, like if you do containers, for example, you usually start out with container version 1, and then you fix something, security bug fix, or you broke something, so you need to fix it. So you do another container version. It's going to be pretty much the same one, right? It's going to be put together from the same Debian packages or RPM packages. It's going to have the same files in it, except for very few that you actually change, right? So in that case, you have lots of different, but very similar trees. Use cases are, I already kind of suggested that it's for West Container IoT VM image delivery, right? It's kind of the same case, right? Like whether you have a VM image, then it's usually like a raw disk image that you have. If you have a container, it's something like a tarball. Yeah, if you, like depending on what your specific use case is, it's slightly different, but the essence is always the same. You distribute a large file system tree across a lot of systems. It's also, one use case is home synchronization, right? Your home directory between multiple machines. I'm pretty sure everybody of you has run into this problem, that you have access to multiple computers and you would like to share the data between them. And the third use case that I care about is backup, right? Like where you could update, like you could synchronize your home directory to some central server in regular intervals and make sure that nothing gets lost. Yeah, let's actually jump in with now what it means on the more technical level. First of all, CAsync is a tool that can operate on two different layers. The first layer it can operate on is the block layer, right? The second layer is the file system layer. What does that actually mean? If you distribute a file system image, right? Like you can send a tarball. That's what I call on the file system level, right? The tarball doesn't have any information if it's backed by XT4 or whatever, it doesn't matter. A tarball just contains files and directories and the contents and the attributes of them, right? But you can also distribute disk images on the block layer, meaning instead of just distributing the files, you actually distribute the whole file system, meaning a block image of the XT4 file system or XFS or whatever you use, right? CAsync is a way how you can distribute these images on either of those two layers, either on the block layer or on the file system layer. What you use is up to you. It has different properties though. So what does CAsync actually implement? This is a very superficial overview about the algorithm in the background. Hopefully, when I explain this algorithm to you, you get an understanding what it actually does, and hence how precise you can actually use it for whatever you want to do. So, first step of the CAsync algorithm is let's serialize all things. On the block layer, that's easy, right? The serialization of the file system on the block layer is just read block after block, DD, right? Everybody of you knows the Unix DD command. What you can do with that is you can read a file or a block device and write it to another file, block by block, right? So that's easy. On the file system layer, it's almost as easy. It's tar it up, right? Everybody of you knows tar, right? What tar does, it goes recursively through a file system tree, and even though this tree might have a tree form, what you end up with is a simple byte-by-byte serialization of the thing. That's what CSync does, but it's a little bit more complicated. We don't actually use tar for various reasons that we're going to talk about, but it's it's doing basically the same thing, right? There's nothing conceptually new at this part. Second step, what CSync does, is it splits off the serialization, right? First step gave us this basically simple file that starts at 0 and then block, 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 or byte, 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 follows to the end. In the second step, we split this up. Specifically, we take the serialization, chop it into a series of chunks, right? In a series of blocks, or whatever you want to call it. But the interesting thing about it, it's not chunks with always the same sizes. Instead, we use variable sizes where the size is picked depending on the chunk's content. The same data should result in the same chunk size, right? So, why that, you might ask? This part is actually the rsync algorithm, just to mention this. The idea basically is this. If you have lots of very similar trees, right, and you change the file somewhere, and you open, for example, a text file, open it in Vim, change something, added like one line at the top. On disk, the difference between the old version and the new version is basically the same file, but somewhere in the middle you added a couple of bytes, the new line, right? So everything before it is exactly at the same location with the same contents. Everything below it, right, after that change, is still the same data, but it has moved a couple of bytes down because you inserted something in front, right? So if we would make it simple and would chunk everything up in the same size blocks, then this would basically mean that the blocks at the beginning would stay the same, but all the blocks at the end would change because always a couple of bytes would be moved out and a couple of new bytes would be moved into each block. What the rsync developers, Andrew Tridgell, like the guy from Sandberg, came up with is this algorithm where instead of doing equidistant cuts, we do cuts that are dependent of the chunk's contents. The idea is that if you have such a text file and you add a line in the middle, that the block around this change will become different, but all the blocks following will be ending up in the same position again. Why again? Adding extra byte at the front shouldn't ripple into all the following chunks, but only alter the local, immediately surrounding chunk. The algorithm that actually happens, if you don't understand this, that's completely fine, but for those who want to know the details, what actually happens there, how rsync implements it ultimately and how we implement it, like we basically use the same algorithms, we use like more modern hashing functions, but still the same algorithm really. So the used algorithm is a hash function called bus hash. It's a cyclic hash function. A cyclic hash function is kind of nice. It basically allows you to hash a byte stream, and at every single byte of that byte stream, it can calculate very efficiently the hash function. You can basically progress through the buffer, and for every byte, very easily calculate the hash function of everything that came before it. That's different, like for example, for a classic hash function, because for normal hash functions that are not cyclic, like you would have to, like after you calculated the hash of the first 10 bytes, and you want to calculate the first 11 bytes, you would have to throw away everything you calculated and start from the beginning, which makes it extremely inefficient. So we use a cyclic hash function, and then we hash the data stream byte by byte, and each time, for every single byte, like for every window that we move around, we get the hash value, and we test it against a specific test, and if the test holds, we make a cut. If it doesn't, we don't, right? The test used is actually h modulo q equals q minus 1, by h being the hash function, q being some parameter that you pick. The essence of this test basically means is by selecting q, you can choose an average, how often you make the chunks, like how many chunks you split your serialization into. Why that matters, we'll talk about later. Yeah, up to this point, we have the serialization, we split it into chunks. That's the first two steps. The third step is, of every single one of these chunks, we now calculate a strong hash function. This is the part where we take inspiration from Git, the content addressable thing, right? We have now a series of chunks. One chunk here which is like 100 bytes, the next one was 150 bytes, the next one was 138 bytes, whatever comes. We calculate a strong hash function, which is by default SHA-512-256. That is that's the SHA hash function. It's actually a little bit like SHA-512, but a little bit shorter. We use that one because it's very fast and 86 to 64, but that's just an implementation detail. The key is though, we have chunked it all up, then we hash all the individual chunks, and then we have the hash values that identify each chunk individually. At the same time as we calculate these hash files, we write out an index file. The index file lists all the hash values of all these chunks, right? So the index file is basically just a long list of hash values. That's what it is, right? Now the interesting thing about the index file is that that is completely sufficient to reconstruct the serialization, right? Because it just uses the hash function, the hashes identify the blocks, exactly like in Git. So if you just retrieve the blocks, you can concatenate it, and there you go, you have the serialization back. The fourth step, and last step really, is to compress each chunk individually, right? And place it in a special directory, which we call the chunk store, which is, it's the repository where we put compressed chunks in, where each chunk is identified by one of these hashes. The file name is actually the hash value, so that, it's exactly like in Git. Yeah, if you ever looked into the details of Git, you will realize that this part is basically Git. And this is what the algorithm does. To recapitulate, what happens is first serialization, right? We take this directory tree or the disk image, make one serialization, we chunk it into pieces, where all the pieces have different sizes, but the sizes depend on the contents of the chunks. Then we hash and index them, like index meaning just writing out the index file. And finally, we compress each chunk and write it to disk. What about extraction? It's simply the reverse. First step, we acquire the index file. As mentioned, the index file describes precisely what the serialization is like. Then we acquire for each of these hashes the chunk. And then in the third step, we concatenate these chunks after uncompressing them in exactly the order in the index file, and we have the original serialization. The serialization we then simply deserialize to disk, right? We write it either to the block device or we basically untar it again. That's what it is. Why is all this interesting, right? Like I told you an algorithm here, and you might not see the actual applications of this just yet. What's really interesting about this is if you have multiple file system trees and you do this with, right, then the chunks will mostly be the same, right, except for the chunks that are located around the actual changes that you make, right? So you have one serialization of my home directory from today, another serialization from the home directory from yesterday, and if you serialize them and chunk them, it will 90% is going to be the same chunks, except for the 10% where I actually make changes where the chunks change, right? So if I now drop all these changes in the same repository, I have perfectly stored the version from yesterday and the version from today, but I only used 1.1% of the data, like the actual repository space, because I could reuse all the chunks from yesterday. For those who know rsync well, the key difference of this algorithm is I don't care about the file boundary, right? Like because rsync is inherently built around the file system boundary or the file boundary. So basically, if you copy with rsync one directory tree from one system to another, it goes through all the files and directories and will implement the chunking algorithm that I talked about, right? The part that is similar to rsync, but will only do that on individual files. Specifically meaning, if you have one file on your file system tree, and that also under the same name exists on the next state, then rsync will start its actual rsync algorithm, and otherwise it won't, right? In my algorithm, because I serialize first, I give up the file boundary first, so I have this benefit that I will actually recognize the same chunks even in different files. If you rename the files, it's completely fine by me, because I actually care about the file contents, and I don't really care how the files are named, because, I first serialize, throw away the file system boundary basically, and then I chunk it out. Now it also has this benefit, it lumps small files together and splits large files apart, right? This is different from rsync, for example, because rsync as mentioned, they care so much about the file system boundary, so they will always copy files individually. So if you have lots of small files, it will do a lot of work, and if you have lots of few files, it will do little less work. And this stuff works differently. It's also different than Git, for example, because in Git also cares a lot about the file boundary, right? Like if you have a Git tree where there are lots of small files in there, you will have lots of objects. If you have a Git tree with lots of big files, you will have very few objects. And this basically also means that in a Git tree, you can share less or more, right? Okay, yeah, our chunks are more evenly sized this way. And yeah, we can recognize similar blocks of different files as well as files renaming and moving. Why do we do all this? I mentioned this already. A similar file system image results in mostly the same chunk files, which means very efficient storage of many related trees. And not just that, it's also about efficient delivery, right? Like because if I already have the home directory from today, and I want to retrieve the home directory from yesterday, I can use all the chunks that I already have in disk and just retrieve the other ones that are different. What's also nice about this is that in contrast to tar or rsync, or rsync actually does provide something like this, but with weaker requirements, there is implicit validation, right? So on access, like every time I unpack one of these directory trees, because I have these strong hash functions in place, and every chunk is identified by these hash functions, I can implicitly validate it all, and hence I know for sure that when I unpack something, that is exactly the version that I actually packed up in the first place, because all the hashes need to match. What's also important is that downloading file system images prepared this way is very CDN, like in content delivery network friendly, right? Because I have roughly the same size blocks, right? This is because, again, I can split up big ones and collapse smaller blocks, and each of these chunks has a very good chance of reuse and is immutable, basically, right? So the idea ultimately is, let's say you build a system where you have lots of containers, and these containers are highly related. They always are, because most people, for example, build their containers from Ubuntu images, and since Ubuntu only puts out a new version every half of a year, probably of all the containers that are out there in the world, they share a very large degree of the same data.